Hello. So in this section, we're going to continue our work on graphs, but now we're going to look at something called graph transformations. So what can we do to basically change what a graph looks like? All right, and you would have seen this at GCSE. And when we looked at how we can translate, so how can we move a graph, how we can enlarge a graph, how we can rotate, and how we can reflect. We'll be primarily looking at translations and sort of enlargement, stretching in this particular course. But the first thing we're going to look at is this translating graphs. Okay, oh, translating graphs, right? So let's take a particular example of a graph, of a curve, of a function. Let's take x squared, right? Fairly nice example. So y is x squared. Okay, and obviously it's going to pass through the origin at 0. Okay, so the first thing we could do to a graph is we can translate. So we can base what translation means is basically can move the graph around essentially. It will not change the shape of the graph in any way, but it will change where it's located and where it is. So the first example is we can move it horizontally, which means I can move it along the x-axis because the x-axis is horizontal, it's left or right. So we can move the graph left or right. Okay, so firstly we could have this sort of graph if we move to the right. And so then that we moved it by a amounts, right? Okay, so we moved it to the right by a amounts. Or alternatively, we could instead move it to the left if I draw it with a different colour by a amounts as well, right? Doesn't matter what a is, it's just a random variable, so that'd be minus a there. So I moved it to the left by a amounts instead. Okay, so there are two possibilities in that respect, and these both are translations. So, and more specifically, they are horizontal translations. Okay, which means we basically move the graph left or right. That's all that means. Okay, and we can do the same for the upwards and downwards as well. So if I then draw another graph, we can firstly move the same graph upwards by a amounts. Okay, doesn't look that similar. There we are. So that would be a there. So that's moving it up by a amounts. Or alternatively, we could move the graph downward by a amounts. So it would look a bit like that. And so then it would pass through minus a there. So that it'll be on the y-axis. So if it's moving up or down, you're moving it up and down the y-axis, okay? And the y-axis, so if I label my axis here, y and x, the y-axis is upwards, so it's a vertical translation that time, okay? And again, what that means is move the graph up or down, essentially, okay? And that means up and down the y-axis, because that's where y acts. Okay, cool. So that's what we're going to look at, right? That's a simple, concise idea of what we're working with in this chapter, right? Moving the graph left to right, up and down, okay? Fairly simple, and hopefully you notice the graph doesn't change its shape. It's the same graph, but it's just moved, okay? I mean, the drawing might be a bit horrible, so it looks a bit different, but trust me, these graphs are the same as this one, they're just moved in different places, okay? And that's what we're going to look at. And we're going to look at how we can kind of do this mathematically. How can we express this? Okay, well, let's have a look then. So, first of all, this horizontal moving left to right, okay? Firstly, well, if we move to the right by a units, so we move to the right by a, right? That's that graph there. We can express this as a so then we can express this in terms of coordinates. So take any general point on x squared, that's xy, right? Any point on any curve, okay? Xy if we want to move it to the right by a units, we're moving it along the x-axis, right, as you can see here. But that means every x coordinate has to be shifted or moved up by a, okay, in order for that to happen. So, as you notice, for example, this point at the origin moved from 0 to the point A, and that's because we added A to the x coordinate, and that applies to the whole graph. Okay, so the new coordinates will be the translated coordinates, will then look like x plus A and y. So the y coordinate stays the same because I'm not changing the y values. I'm just because I'm not moving it up or down. I'm just moving it left or right. Okay, so that's how we can express it. Or you might see it as a vector 0a, which means no a0, because obviously a vector looks like xy, which again just means we're moving it to the right by a units. Okay, if you want to move it to the left by a units, that's sort of the negative direction. Okay, because think about the negative x-axis is to the left, so instead we would say x to y would then go to, and you'd subtract the x coordinates, right, if you're going backwards. So x minus a to y if you want to shift it to the left. And again, you can notice that here with this graph, where again here we start from 0, and then that same point gets translated to minus a, so we've gone backwards, but so we subtracted a, so get minus a. Okay, cool. And then if we want to move up by a unit, so we're going to look vertically now, so this graph firstly. If we want to move up by a units, we again take any point x, y, and then that translated point would go to x, because again the x coordinate will stay the same, because we're not moving it left or right, we're just moving it up. And then if we're moving it up, we're moving it up by adding a amount, so it'd be y at plus a, okay? And you can see that here, because this point here is 0a. So we went from 0, 0 to 0a. So we added a to the y coordinates, and that would be for every point on the curve, right? We add in a to every y value to get that to make it move up. And vice versa, if we're going down by a units, that's going downwards, that's a negative y axis, so we're going to be subtracting a instead. So any point x, y would then go to x, and then y subtract a to make the y values would go down, so the graph goes down. Okay, so that's generally what we're doing, right? That's how we shift these curves, by adding a number to the coordinates. So if we want to move it along the x-axis, we're going to add or take away the a, depending if we want to move it right or left. Likewise, if we want to move it up or down, that affects the y values, because that y acts up and down, right? We add or take away a to the y coordinates. That's essentially what's going on there. Okay. Okay. So then, okay. So then, what can we do next? So, there's something more interesting to this. Something more to this, and notice as well, we can write these what's it called? These curves, right? These as functions, right? We can alternatively say f of x is x squared, right? And that will be helpful in a minute, because again, I mean, it's okay for one particular point, knowing you need to add a, right? But any curve as infinite points, right? Really, so you can't just do this. You can't just add a to every individual point. That'd be too cumbersome. What we instead use is the whole function itself, right? And so what we now look for is an expression that basically what we want to look for is, again, we want an expression for f of x for all these different curves here, instead of just mapping each individual point one by one, right? So we want to find a simple way of getting an expression for all these translated graphs, right? Because then obviously if you have that function, we can then work out all the roots, the y-intercepts, and all the details we know and love about all these type of graphs. So we have an expression for the curve for those translated points too, without having to again add the coordinates to every single point. So what I'm saying here is I want to express this in terms of f of x, right, to all these new curves, right, which should get me expression for these. How am I going to go about doing that? Well, let's think about it. Let's consider horizontally first of all. So horizontally, well, we want to move it again, x to y. We want to move it to the right. Okay, so we want x, y to go to the point x plus a, y. So we want to move it to the right by a amounts. Again, that's what we talked about here, right? This first statement we did, right? So I want to move it to the right. Want to add the x coordinate. Want to add a to every x coordinate. Okay, so that's what's going on there. Okay, now I already said I want to have a function expression for the new curve. Okay, so our original curve was y is f of x, right? Any curve at all, f of x is applied to any curve. Okay, well then what happens if I plug in the new input? If I then plug in the new input, I get y is f of x plus a, right? Because the input is now x plus a, not x. However, what's the problem here? Well, the problem here is the y coordinate, the y value has to be unchanged, has to be remain intact, because I'm not changing the y value, because I'm only moving it right or left, but it's not going up and down. So the y value has to be the same. However, here originally y was f of x, but now I've changed the y value to be f of x plus a. That will give a different output. Remember when we looked at functions, if you have a different if you change your input, you're probably gonna get a different output. Okay, so the inputs change from x to x plus a, so our output will be different. So this y value will not be equal to f of x plus a, because y is f of x. Okay, we need the output to remain as f of x. Well, how are we going to do that then? So I want it to be y again, but instead what I need to do is I need to counteract this new input. Well, if I have x plus a, I want it to go back to x to keep the input to match f of x. How am I going to do that then? Well, I can just take away an a, okay? Then the a's cancel and we're left with f of x. Well, ding, 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 I now match the y value to begin with. So now the y values now match, okay? What that means is then as a result is that I need to, whenever I apply a translation horizontally, I need to account by subtracting a. Okay, so if I have an original function therefore of if I had y is f of x, that means instead that if I have f of x minus a, that means I'm shifting the original curve f of x to the right by a units. Okay, so essentially it's kind of like the opposite. So you'd think if I have f of x, if I'm then plugging in x minus a instead of x, you'd think, wow, I'm subtracting a to the x values. But and therefore we saw that if we subtracted a, it actually moved the curve to the left, right? But that's not what's going on, because actually the opposite's happening. Remember, if I have f of x minus a, as we just saw here, that actually corresponds to adding a to the x coordinates. Okay, so this minus a is adjusting for the fact we need to keep the y value the same, which means then it's the opposite. Okay, so we oppose it, so we do the opposite. So essentially all this means is if I have f of x minus a, that means we need to move the curve to the right by a units. Okay, cool. So as an example then, if I had Let's say I have this again. F of x is x squared, right? If I then wanted to plot f of x minus 4, well, instead of moving to the left, but you wouldn't subtract 4 as it suggests. You do the opposite. So instead you add 4 instead. So you move 4 to the right. Okay, so it'd be looking like this instead. That would be the new curve, f of x minus 4. Okay, so you'd move to the right. So if you're subtracting, you do the opposite, and instead you add. So you move it 4 to the right. And we will look at examples like this to really demonstrate what this means in a minute. Okay. But then what about if we move it vertically instead? Well, again, vertically, if I'm moving it, say, up by a units, then our point x, or any point on the curve xy, we want it to go to x and then y plus a. Because then if I'm adding a, again, if I'm adding a to the y values, I'm shifting it upwards by a, which is what I want, to move it vertically up. Okay. Again, how do I do that as a function then? So originally, again, with this original curve, y is f of x, right? Then, this is saying, I'm doing y plus a, right? And then that would be equal to f of x plus a, right? So there we are. So my new, I don't have to do anything here because then y, the new y value, because y, I'm literally substituting in y there. So this is the new output, right? Y plus a, that's the new output. If you're happy with that, right? So the new output, the new y value is y plus a. That's what we want. That's the translated point. And so therefore, and then I'm substituting in y here. That's what I'm doing. So then y is simply f of x, add the a at the end. Well, that's great news because that means that in this case I don't have to do any sort of corrections because my input stays the same. It's still x, right? But that's what I want. I want my x to stay the same. I want the same input when I translate it vertically, because if I move it vertically only, I'm not moving it left or right, so the x value should stay the same. So in this case, vertically, x stays the same, so I don't need to do any adjustments. So literally, as it says in this case then, if I have y is f of x, then f of x plus a number outside the function, means what you expect. So then you move the curve up by a units, okay? Because it makes sense, right? Because then in this case, if you're adding a amounts to the y value, you are shifting it up by a, which is exactly what you expect, okay? Cool. Okay. So overall then, yeah, it's not gonna let me. Overall, I'm gonna get rid. Let me get rid of this now. This bit, and also, by the way, this applies to. Let me go down. These two statements here apply to left and right as well. Except the only thing you have to just flip the negatives. Okay. So instead of, if we wanted to move to the left, we would have f of x and plus a instead, because then that would maybe move minus a units to the right, which means a units to the left. Okay. But we'll see that in action in a minute. But overall then, what that means is, hopefully you see that horizontally, when we affect the x values, it does the opposite to what we expect. So instead of subtracting the x, if we have a function, right, what we do inside the bracket is opposite to what we expect, right? So in this example, again, if we're doing x minus a, you'd think we'd be subtracting a from the x value, so we move it to the left to be more negative, right? When in actuality, as we saw, this means we're actually moving it to the right in the positive direction, so we're adding a units to the instead to all the points to move it to the right. But vertically, everything acts as you expect, okay? Because and then if we're adding a number outside a, that's exactly what you expect. The y value is going up by a, okay? So it moves up. And likewise, if we did f of x minus a instead, you're just going down. So because you're subtracting a to the y put for y values instead. So yeah. Overall, then, we can summarise all this by and this observation by if I get rid of all this, do, 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 by noting this observation is uh, what we do. What we do inside the function f of x. So remember our original function, it will always be f of x, the original graph, and then before we translate it. What we do inside the function f of x, which is the input, remember, or the x, that's inside the function. We do the opposite to what we expect. So what I mean is, again, as an example, f of x minus 2, say, means adding 2 to the x values, which means shift graph 2 units to the right. Okay, because adding, remember, makes the x values more positive, so it goes along the right side of the x-axis, so it moves it to the right instead of subtracting. And then oppositely, then what we do outside the function, that should be inside the function, outside the function, f of x, which is now our output, remember, or our y values, we do exactly what we expect. So again, as an example, if we then said f of x plus 2, and remember this plus 2 is outside the function this time, it's not inside the function in the bracket, so it affects the y values, okay, because the input isn't changed. So f of x plus 2 means adding 2 to the y values. So we're going to shift graph 2 units up. There we are. And I am going to box this if I can, because I think that's the most essential idea when we do any sort of graph sketching. These two ideas will be absolutely helpful and pretty much crucial. Okay, these two ideas, okay? So the idea that essentially overall, and we will look at more graph transformations next time, and it will be the exact same philosophy. Whatever we do inside the function to alter the input, so anything inside the bracket of f of x, affects the x values, and we do opposite to what we expect. But then outside the function, so if anything is outside the function, that affects the y values, and that does exactly what we expect. So we will look at examples now that will really demonstrate this idea, and hopefully it will make a lot more sense as we look at examples. Okay, let's have a look then. Oh dear. Okay, let's have a look at the example then. Firstly, it wants us to sketch the graph of y is x squared. Well, that's a standard graph. Hopefully we should know. We looked at the quadratic graphs earlier in the course, so it looks simply like that. Okay, so it touches the origin, and then it goes like that. Cool. Then part B says sketch y as x minus 2 squared. Now what you could do, you could just expand it and then get a quadratic, and then you could sketch that quadratic using the ideas that you've learned about sketching quadratics. So you find the turning point to find the minimum, you find the y-intercept and the roots, and then all go from there. But that can be a lot of work, right? But we can really cut down on the work by realising if we called f of x is x squared, well, notice the difference between these two, all the similarities even between these two curves. They're x squared, but our inputs change. In this one, we're doing x subtract 2. So part B, our new y, is f of x minus 2, isn't it? And that would be x minus 2 all squared. That's the curve we have. Well, hang on a minute. We know what this means if we are subtracting our input. What does that mean in terms of transformations? So we know f of x minus 2. Well, you'd think you'd subtract the x coordinates, right? So you move it 2 to the left, because obviously that's where x, you make it more negative if you move a graph to the left, because the x coordinates will get smaller. Well, actually, it does the opposite to what we expect, and it affects the x value because the minus 2 is acting inside the bracket. That affects the x. So that actually means we shift graph 2 units right, okay, not left, right, because as again going to the right is along the positive x-axis, so you're making it more bigger, so you're adding 2 to the x coordinates. So therefore our graph then, with that in mind, well, instead of 0 this time, this point 0, 0, the origin, we're going to add 2 to the x to that value, so a new turning point would be at 2, 0 instead. Okay, so the x value would be 2 instead of 0. So hopefully you see what that means by the idea of adding numbers to the x coordinates. So now we're adding 2 instead of subtracting 2. So we do the opposite to what we expect. And then our graph then shifts to the right as so. Okay, there we are. Cool. And now actually this graph would also pass through and cut through the y-axis now as well at somewhere that isn't the origin. So how do we then find the y-intercept? Well, the y-intercept again occurs when x is equal to 0, right? So then y, well, a y is now this, so x minus 2 squared. Plug that in, you get 0 minus 2 all squared. That it would be positive 4, so that would be 4 there. Okay, the y-intercept. But yeah, cool. So that's just shifting the original graph by 2 to the right. Okay, let's have a look at part C. Part C. Again, now it's saying y is x squared plus 2. Again, you could sketch that quadratic using the tools that we've learned already by completing the square, finding roots if applicable, the y-intercept, so on. But again, notice it's helpful to consider it as transformations. So what have I done compared to the original graph? I've just added 2. Well, hang on there, and that's saying basically f of x plus f of x then plus 2 outside, right? Because f of x is x squared. So I recognise this now as what? What is this transformation representing? It's outside the function, the 2, so it's going to affect the y value, so it's going to go up or down, okay? And it's going to go up because we do what we expect, we add 2, so it's going to go upwards. So it's going to shift the graph up, and the graph is the original graph, x squared. So the graph x squared up by 2 units. Cool. So then that graph would look like this. So if we're moving it to the 2 units up, so we're moving, remember this graph x squared is 2 units up. So instead of passing through the origin, it's going to pass through 2 here. Okay, and that'd be the new turning point. Cool. There we are. Great. So hopefully started to build a sort of vague idea now, but let's have a look at more examples to hone in on this. So we're given f of x is x cubed, and g of x is x of x minus 2. We want to sketch the following graphs, indicate any points where it crosses the axis. So firstly, it wants us to sketch y is f of x plus 1. Well, again, notice hopefully this is going to be a transformation. It's acting inside the function. I'm changing it inside the function, so it's going to affect the x, the input, the x values, and because it's affected, because it's inside the function, it's going to do the opposite to what we expect. So instead of adding 1 to the x values to shift it up by 1, we're going to do the opposite and actually subtract 1 to the coordinates. So it goes to the left, to the negative x side, right? So, okay, well, before we sketch this one, we need to look what the original graph looks like in order to translate it, right? So what does f of x look like? Well, x cubed, we should know what that graph looks like. It looked like this, right? So again, very standard graph. Okay, with that in mind, then I can have an idea about what to sketch for f of x plus 1. Well, f of x plus 1, again, it does the opposite, so we're going to shift that original graph left, right? Because that's where, again, x is negative, right? So shift that to the left by 1 unit, okay? Which is the same as essentially subtracting 1 to the x values, okay? Remember? So that's what we're going to do. So shift the whole graph 1 to the left. So instead of going through 0, it's going to go through -1 there. But the graph will have the same shape and everything otherwise. So it's going to go through it and look like this. There we are. Cool. And obviously this time now there's also going to be a y-intercept that isn't at 0. So we need to compute that to sketch the graph. Again, the y-intercept is when x is 0. Okay. Then the y-intercept when x is 0. Well, what's y in this case? That graph is f of x plus 1. Let's substitute x in 1 into that. So if we have f of x plus 1, but x is 0, so 0 plus 1 is f of 1. Okay, but f of 1, well, f of x is x cubed. So plug in f of 1 into here to get 1 cubed, right? So that'd be 1 cubed, which should be 1. Okay, so again, it would pass through the y-axis at 1, and that'd be the y-intercept. Cool. Part B then, it's asking to sketch g of x plus 1. But before we do that, hopefully again you recognise it's going to be a transformation. And it's going to be a shift 1 to the left, okay, in the x direction. So, well, in order to do that, we need to know what the original graph looks like. And again, hopefully you recognise this is going to be a quadratic graph, okay, because we're going to get a quadratic term out of this, of x times x. So again, we're going to sketch the quadratic. So firstly, we need to know the type of shape. Is it a smiley positive shape or a frowny negative shape? Well, the coefficient of x squared is just x squared, so it'd be 1. That's positive, so it can have a smiley U shape. Then we need to determine the y-intercept. Well, that's when x is 0, for it to be on the y-axis. So if x is 0, then the whole thing's 0, because there's an x there. Plug in 0, the whole thing's 0, so it's going to pass through the origin, okay? Then lastly, we need to find the roots. So the roots are when the whole thing equals 0. So either x is 0 or x minus 2 is 0, which means x is 2. Okay, so it's going to pass through 2 there. So therefore, then, with that shape in mind, it's going to look like this. There we are. Nice. So that would be y is x of x minus 2. Cool. So that's the original graph. Then it's asking us to sketch y is g of x minus 1. Plus 1, sorry. But that's going to do the opposite again. So if it's inside the function, inside the brackets of the function, it does the opposite to what you expect. So you'd think you'd add in 1 to the x coordinates and move it to the right, but actually do the opposite and go 1 to the left instead. So that is a shift of 1. So you shift the graph to the left by 1 unit, okay? So the left is the negative direction again. So this whole graph then needs to move 1 to the left. So it's through our axis, and that should be y and x. So firstly, in order to help sketching graphs like this, is what you can consider firstly what the particular point is mapped to. So these two roots are going to be quite interesting. I know what these roots are. Well, firstly, the first root I've circled here is the origin 0, 0. Well, if I'm moving 1 to the left, 0, 0 is going to go to minus 1, 0 here, isn't it? So that is going to be it's going to go through minus 1 instead. That's the new root. Then this 2 again, this next point is going to move 1 to the left. So it's going to go to 1, 0 here. And there we are. So the graph then, passing through these two new roots, will look like this. Okay, and we can also find the y-intercept, actually, can't we, for this as well? Well, the y-intercept, again, would be when x is 0, y would be, well, y in this curve is g of x plus 1, right? So if I sub in 0 for that, I got g of 0 plus 1, which should be g of 1. Okay, so then what's g of x? Well, that's this original curve here, x of x minus 2. So if I substitute 1 into that, I get, well, 1 for x, and then x minus 2 would be 1 minus 2. That'd be 1 lots of minus 1, that'd be minus 1. Okay, therefore the y-intercept here would be minus 1. Okay, and the root there is also minus 1, although it looks a bit awkward. There we are, so that's that curve then. Cool. Then it's, in this example, given that h of x is 1 over x, sketch the curve with the equation y is h of x plus 1, set the equation for any asymptotes and intersection with the axis. Okay, so just sketch the graph. So we need to sketch this graph. Okay, so y is h of x plus 1. H of x and then plus 1. Right, again, what's happening to what's happened to this graph, right? In terms of h of x, the 1 is outside the function. So it's going to affect the y value, okay? And if it's outside the function, you do what you expect, okay? So the y values, if you're affecting the y values, you do what you expect, okay? So what I expect is I add 1 to the y coordinates to move the graph up by 1, and that's what I'm going to do. So this is a shift of the graph, and the graph is 1 over x, right? That's the original graph, up by 1 unit. Okay, well, I need to know what this graph looks like, 1 over x. But again, y is 1 over x. That's a standard graph you need to know. We looked at that a few videos ago. It was early on in the chapter. That's a reciprocal graph, remember? So, firstly, 1 over x, when x is positive, when x is close to 0, it's going to go from positive infinity. And it's going to come down, and then when x goes to infinity and gets larger and larger, it goes to 0, okay? And remember, there is an asymptote at 0, okay? And actually, there's two asymptotes, because horizontally on the x-axis, it's going to 0, right? So the horizontal asymptote, remember we covered that. It's going to be x is 0. But so again, as a reminder, asymptotes of what a function or a graph likes to tend towards, but it'll never meet. So it's tending to 0 here, right? But it's never ever going to actually touch 0 on the x-axis. Okay. Then there's also a vertical one. Remember as well, where vertically is on the y-axis, and as you see here, it's tending towards y0. No, hang on. No, x would be 0. And then this will be y0, sorry. Okay, because the vertical asymptote is basically the y-axis, which is when x is 0. The horizontal one, which is the x-axis, is when y is 0. And then obviously when x is negative, then it goes from negative infinity. And then as x gets larger to negative infinity, then it goes to 0 as well. So those are the two asymptotes. Why am I writing the asymptotes is because the question asks you to state the equations of the asymptotes. So, yeah, but it's also a good idea to mention all the details of the graph if you can. Anyway, so that's my original graph, and then I've said that h of x plus 1 here is a shift 1 unit up. Okay, so that's what I'm going to do. I'm going to put the whole graph up by 1. So then y is h of x plus 1 is going to look like this. Well, firstly, it's going to tend, well, instead of tending towards 0, it's now going to tend to 1. The asymptotes firstly are going to move, well, the y values, right, are being increased by 1, so the graph is moving up. So that means the horizontal asymptote at y0 is going to move up by 1 to this, okay? 2 y is 1. That's the new horizontal asymptote, okay? And then again, it's going to tend towards 1 on the positive x side, as so. And then this graph, this part of the graph, is also going to move up by 1. So instead of going towards 0 again on the x-axis, it's going to shift up to tending towards 1. So it's going to look like that, okay? So there we are. Cool. And the vertical asymptote at x is 0, remember, which is the y-axis. That's going to remain unchanged because it's x is 0. I'm not changing my x values, remember. I'm just shifting it up. So the x, so the y values change, but the x doesn't. So overall, then the and also the horizontal asymptote. Well, that's now going to be y is equal to 1, which is this line, this dotted line I drew here, right? There. And by the way, it's a dotted line because if you remember back to inequalities, remember we draw a dotted line if we want it to be strictly less than. The whole idea is that we do not include the actual value into the line. So in this example, I don't want the curve to be equal to 1 because that it can't be 1, okay? Because again, if this is saying if y is 1, then 1 will be 1 over x plus 1 because that's h of x, right? Is 1 over x. Well, then 1 over x is 0. You can't. There's no solution to this, so it cannot ever equal 1. But yeah, that's why we have a dotted line, to exclude the possibility that the curve can equal 1, okay? Because it tends to 1, but it can't be 1. It's the whole idea of an asymptote, right? Anyway, and then the vertical asymptote will still remain x is 0, okay? Okay, but then it's asking for the points of where it intersects the axis. So I noticed it intersects here, the curve at this on the x-axis at this point. How are we going to find that point? Well, this is a root, right? And remember, roots are when y is 0. Okay, so y is 0, and remember y here is h of x plus 1. So that means 0 is h of x plus 1. But again, I remember h of x is 1 over x plus 1 equals 0. Then 1 over x is minus 1. That means then if I times across, x is going to be minus 1. Okay. There we are. Well, actually, no, technically, if you times across, minus x would be 1. But then x would be minus 1 if you flip the sign. So anyway, this point is at minus 1. There we are, cool. And that's the only intersection of the axis, right? Okay, cool. So I think you start to get a flavour of what we're doing here with the translations. And the whole idea that what we do inside the function, we do the opposite. And then what we do outside the function, we do what we expect, and that affects if it goes up and down. Anyway, this example there, we need to sketch the graph of y is x of x plus 1, x plus 3 all squared. So again, that is going to be a quartic, which we should know how to sketch, right? So first you need to consider the type of shape. It's going to be a positive shape like this, or a negative shape like that. Well, let's look at the x to the 4 power. So we're going to get x times x here, times x squared, because this will be the same brackets wise. That will give me x to the 4, so it have that sort of shape, right? A W-ish shape. Okay, now I can draw my axis, as so. But then I need to find some information. I need the y-intercept and the roots. So the y-intercept firstly is when x is 0, then y would be 0 as well, right? Because if I plug in x 0, the whole thing becomes 0 because I'm multiplying everything by 0. Anyway, so it passed through the origin there. Then I need to find the roots. So that would be when you set the y equal to 0 instead, which would mean the whole thing equals 0. So I have to put each part of x equal to 0, so each bracket. So either x is 0, which is the origin, or x is minus 1, which should be there, or x equals minus 3 to set that last bracket equals 0, so it'd be about there. Okay, cool. Okay, lastly, I need to tell what type of roots we have just to see exactly how the curve will go. Well, the first two are what we call single roots, remember. The brackets are just linear. The brackets only appear once, right? There's no squaring going on. It's just x is 0 and x plus 1 is 0. So they will, if they're singular roots, remember, they just pass through. They cut through the axis at a point, okay, as like that. Then the last root is a double root. X minus 3 is a double root. It's a double repeated root. because it's the same factor twice, okay, because there's a squared there. So that means it has to touch the axis again, as we covered. Double root like this has to touch the axis at the point. There we are. So with that, all that in mind, and it has to look like a W shape, our graph is going to look like this. It's going to come down from infinity. It's going to touch the axis. There we are. That's going to go down again. Do that again. Then it's going to go up. There we are. Cool. That's what our graph will look like. Cool. And again, we looked at quartics, so make sure you are comfortable with sketching them. We did look at that earlier on in the chapter. Then part B then says, find the possible values of B such that the point 2, 0 lies on the curve with equation, do part B here, y is equal to x plus b plus 1, x plus b plus 3 squared. Okay, so what is going on here? Okay, so first of all, with this type of question, compare what you've got to the original question. So here I have this curve x plus b plus 1, x plus b plus 3 squared. It resembles this. Hopefully you can spot that, right? Let's actually compare exactly how they're different. So first I have x here, then I have x plus b, then I have x plus 1. This is x plus 1 plus b. Then I have x plus 3 squared. This is x plus b 3 plus b squared. What do we notice from that? Well, all I'm doing is I'm adding b to every x value. But then if I'd called this f of x, right, the original graph, well, isn't this just f of x plus b? No? Hopefully you can spot that then. If this is f of x, all I'm doing, the difference with that and this graph, this new graph, is I'm substituting instead of x plus b, okay? Because every x has a b next to it as well, okay? Well, what do we know? What do we notice about this? What do we notice about this function here? Well, again, it's a translation because I'm adding a number inside the function, and again, what I do inside the function, I do the opposite. So here, you'd think I'm adding b to every x value, right? But instead, I'm going to move it to the left instead. So I'm gonna this means a shift. So I'm going to shift the graph, the original graph which was sketched in part A. Remember, b units left, okay, to the left. So it's going to go backwards. Okay, so that's what's going on. This new equation represents shifting the graph, right, horizontally, left or right actually. Why could it be right? Because what if b is negative? Then I'm going to have x minus some negative number. But then if that means I'm adding it, so it's going to go to the right. So actually, depending on what sign of b I put in, if b is positive, it's going to go to the left because I have x plus a positive number. But if b is negative, I'm going to have x minus a number instead. So that's going to do the opposite. Instead of going to the left, it's going to go to the right. So what I can do here is basically shift the graph to the left or right, okay? Now, with that in mind, this graph I've already done is going to be very helpful because then I can visualize, if I can visualize moving the graph left or right, okay? Now, I'm also given that this point 2, 0, this point 2, 0 has to lie on this new translated curve. Well, let's put this point in the original curve. So 2, 0 is going to be there, right? 2. That's where I want the curve to go to. So basically, I need to visualize moving the curve left or right in order to then pass through here, okay? And you can try and visualize it yourself. Okay, so how are we going to do that then? Well, it's on the x-axis, isn't it? So if I'm moving the graph only left or right, well, that means the only way I can hit 2 here is by moving these or translating these roots here, the original roots, to then be that root there. So what that means is, firstly, I need the first root 0, 0, right? I then want that to go to 2, 0, okay? Well, how am I going to do that? Well, notice here, I need to add 2, right, to the x value. So add 2 to x. Well, okay, so then, if I'm adding 2 to the values, I need to subtract 2 in the function, okay, to get that effect. So if I first want to shift 2 to the right, for this first point at the origin to move to this point instead on the x-axis, to move 2 to the right, I then need to do x minus 2, because remember, what I do in the function, I do the opposite to what I expect, okay? So instead of adding 2, I need to subtract 2 in the function, okay? Well, then that would mean b would be minus 2 then, okay? And that goes what we said before, that if we set b to be negative instead of going to the left, that indeed would shift the graph to the right. Okay, then we could do the same for the other points then. So the other points we have are this root as well, minus 1. Well, again, I can only shift it left or right. I want to move it to the right, right? In order for the minus 1 to then go to 2, right? I'm going to shift it this point in minus 1, 0 to 2, 0. So hopefully, again, and you can spot this, hopefully if you visualise it, I'm going to need to add 3 to the right. So I'm going to need to shift 3 to the right. Okay, 3 units to the right. But again, if I want to move 3 to the right, I need to add 3 to get from minus 1 to 2. But then I need to do the opposite in my function. So x minus 3 is what I want to then say shift 3 to the right, okay, to add 3 on. So that would mean in this case, b would be minus 3. Then lastly, the only other possibility to get from a point that's already on the x-axis to move to 2, to shift, it's going to be this point here, right? This minus 3. That's the last point that's already on the x-axis, that then I can shift it right to then map it onto 2 there. So then I want to go from minus 3, 0, the point minus 3, 0, to the point 2, 0, okay? Well, again, what's that going to do? I'm going to need it, how many units to the right? How far do I need to move to the right? 5 numbers up, right? So it's going to be 5 units. So shift 5 right, okay? Well, again, if I want to add 5 to get from minus 3 to 2 to move it 5 right, I'd need to do the opposite. Instead of adding 5, I need to subtract 5 in the function, okay? Which will then give me moving that original graph f of x up by 5 units to the right. And then the value of b to get, because then it's x plus b, which represents this, is going to be b is minus 5, okay? And now there we are. So those are the possibilities, okay? So then it says find the possible values of b for that to happen, to translate the curve to then go through this point. And yeah, there we are. Cool. Then we've got a challenge, which honestly is far easier than the question we just did. But let's have a look. The point R, which is R is equal to 6 minus 4, lies on the curve of equation y is f of x. State the coordinates that point R is transformed onto the curve with equation y is f of x plus c, and then minus d outside. So basically saying transform this curve using this new function, okay? Well, again, they're not given a graph, so we can't visualise anything. But what you should know is, firstly, f of x plus c. Let's break it down. F of x plus c. What's that going to do? You'd think we're going to add c to the x value, but actually we're going to do the opposite. So whatever we do inside the function is going to do the opposite to what we expect. So instead of adding c to x, we're going to subtract c from x, okay? And then lastly, I have this minus d outside the function bit. So anything outside the function itself is going to affect the y value. And then in this case, I do what I expect. So if it affects the y value, you'd expect it to subtract d from y. that's what we're going to do. So then if I have then f of x plus c minus d, then it's going to subtract d from y, okay? Cool. Or you could think of it as adding minus d, but then add plus minus d is minus d. Anyway, so that's basically what we're going to do. So therefore, with these 2 points that I've just done, 6 minus 4, firstly, I need to subtract c from x because I have f of x plus c, so I do need to do the opposite what's in the function itself. So 6 minus c will be the new x value. Then for y, I then said I need to subtract d from y to get the transformation. So then I do y minus d, and that'll be the new transform point. But y was minus 4, wasn't it? That's the original y value, so minus 4 minus d. Okay, cool. There we are. So hopefully you see what we've done there, right? Again, hopefully you see what we've done with this whole video. Is that basically we just applied the original philosophy that we discussed up here. That the points that I've boxed in here is that essentially what we firstly do inside the function, which is the input or x, we do the opposite to what we expect, right? So again here we do x minus 2. We don't subtract 2 to x to move to the left. We instead add 2 to x to go to the right. Then what we do outside the function, so we do exactly what we expect, and that will affect the y value. So if I have f of x and plus 2 outside the function, you'd expect it to add 2 to y values, and that's exactly what it does. So we add 2 to y to get this shifting up effect, which you can see here, right, from x squared. So we shift it a units. But there we are. Cool. I'm going to leave off with a final exam question then, to really demonstrate this. Oh, if it lets me. And it's this question here. So firstly we're given f of x is 2x cubed minus 13x squared plus 8x plus 48. Then given a sketch of the curve there. And it says figure 2 shows a sketch of the curve. And it says part C firstly. Deduce given reasons for your answer the number of real roots to the equation 2x cubed minus 13x squared plus 8x plus 46 equals 0. Okay, so hopefully I'll give you some time to compare and look what we've given. But I will note before we jump into is actually in part A and B, we had to work out that the roots where it passes the x-axis is 4 and minus 1.5. That will be helpful in the question, either part C or D. But we don't know. We don't have the tools if we only studied up to chapter 4, where we're at now, to actually answer that question. But that's not the point of this. I want to look at part C and D, which is relevant to what we just looked at. Anyway, so hopefully I had a look at that. So, okay. So you might think, well, these are the same equations, right? What's different? Surely the number of real roots is just how many times it crosses the x-axis. So it's 2 times. However, this is where you got to look carefully. Compare closely what we've got. I have 2x cubed here, 2x cubed there, right? Then I have minus 13x squared and minus 13x squared. Yep. 8x. 48. 46. Oh. That's a bit different. Okay, so it's not just looking at the graph, because they're technically different graphs, okay? But it's still quite similar, so we can use this original function. So a tip again, if you've got a question like this, let's okay, we have 2x cubed minus 13x squared plus 8x plus 46 equals 0. Well, try and substitute the original function in. So firstly, we're going to have 2x cubed minus 13x squared plus 8x plus 48, okay? That will be f of x, okay? Cool. Okay, but that's plus 48. I want to get to 46. So then I need to subtract 2, right, to get to 46. And that will then equal 0. Cool. So then I'm going to rewrite this to say f of x minus 2 is 0. Because, again, this whole first part was f of x. That's what I substituted in. Well, then Okay, but then what do I notice here? I have f of x minus 2, right? Well, what is that? If I said this is y is f of x minus 2, that's a transformation, that's a translation, isn't it, that we just looked at? We have a minus 2 outside the function expression. So it's going to do what? It's going to shift the graph down by minus 2. We do what we expect. We subtract all the y values by 2. So we're going to go down the y-axis by 2. So graph is going to shift down by minus 2. Okay. So let me get rid of this. So it's going to shift down by minus 2. So it's going to look like that. Okay, so there we go, that'd be f of x minus 2, right? Now, it wants f of x minus 2 equals 0, so that'd be y is 0 in this case, right, if y was 0. But that's corresponding to the roots of this new graph here, okay? So therefore, if we have a sketch of the graph, then the roots of this new graph, when it equals 0, corresponds to the roots of that new equation, right? Well, how many roots are there in this new graph? Well, where does it cross the x-axis? Here, here, and here. And by the way, if you are really unsure, we should be a bit specific here. You might think, well, what if this y-intercept is less than 2? Because then we can't say for sure it still passes through here on the positive y-axis. But what's the y-intercept of the original graph here? It's going to be when x is 0, so it's going to be 48, okay? So it's quite high up, so shifting down by 2 is not going to do very much to the graph. It's still going to remain above the x-axis, really, right? I just thought I'd explain it to be really, really like rigid with the answer. So the graph will indeed look like this. Well, actually, if we're shifting it, but if that's 48 and we're only going down by 2, if you want to be really accurate, the graph's going to be still pretty close to it, isn't it, really? So it's going to look a bit like that. There we are. And then, likewise, continue on the graph. Look like that, okay? Yeah. So then the new y set be 46, right? Because of that'll be when this that'll be the y set to 46 there. So which corresponds to shifting the graph down by minus 2. Okay. So the new y set to 46. Anyway, that's just adding to the graph. But hopefully then you can spot how many roots are there to this new that equals y. How many roots are there to this new function f of x minus 2, to this new graph, translated graph, 2 downwards? Well, that's where it crosses the x-axis. So again, it's going to be here, here, and here. So 3 times. So therefore, there are 3 intersections with x-axis, or you could just say the roots, right? Of the curve y is f of x minus 2. So therefore, there are 3 real roots to the equation 2x cubed minus 13x squared plus 8x plus 46 equals 0. Okay, because remember this equation, again, as we've done up here, this equation is the exact same as this equation if I substitute f of x in, and that is the same as this curve here, so I've done nothing wrong there. So it's all above board. And so that I should say that which comes from f of x minus 2 equals 0, okay? That's where that equation comes from. So therefore that means the number of real roots to that curve are drawn here, f of x minus 2, corresponds to how many roots there are to this equation, basically. So I'm just being a bit precise. Anyway, cool. Hopefully that makes sense. Part D. And then it's saying, given that k is a constant and the curve of equation y is f of x plus k passes through the origin, find the 2 possible values of k. Okay, well, firstly, we have y is f of x plus k. Well, hopefully, again, you should hopefully notice what that's doing. What does this mean? Well, it's a number inside the function, so I'm adding a number, I'm adding something to x inside. So anything inside the function is going to do opposite to what we expect. So instead of adding k, we're going to then subtract k. So it's going to probably move to the left, right? So that's going to be a shift. So we're going to shift the graph k to the left, right? Okay. And so let's read again. So k is a constant, and this curve, which we know what that does now because it's a translation, it has to pass through the origin. So find the two values of k. Well, again, that's going to that actually resembles the question we just did earlier. So we want this translated curve to pass through the origin, right? So let me get rid of this to make it more neat again. So it's going to have to pass through here, right, the origin. So so again, let's discuss. So this f of x plus k represents a shift k to the left. However, if k is negative, if I'm moving minus k to the left, well, that's equivalent to k to the right. Okay, so depending on if k is positive or negative, if you had f of x plus 1, for instance, if k was plus 1, it would indeed move 1 to the left. But if I then set k as x minus 1, so k is minus 1, it'll then shift to the right instead by 1. So actually, it doesn't matter what k is, if it's positive or negative. This means I'm shifting it ultimately left or right, okay? The original graph that they've given us. So how am I going to move this graph left to the right and then make that new graph pass through 0? Well, it needs to, so these roots here, where it crosses the x-axis, it needs to move to 0, right? So it's going to have to move that way, or in this route it's going to have to move down there to the left to the origin, okay? So the only way I can get the new curve by moving the original curve left or right only to then pass through 0, 0, the origin, is to move these points already on the x-axis to 0, okay? Okay, well, what are these points? Well, that's why you need to do pi and b. These roots are 4 and minus 1.5, so we do have values for them, okay? So then we need to basically move 4 to 0, because we could then that mean you'd be shifting it to the left, the curve, or minus 1.5 here, and we need to move it to the right by 1.5, okay, to get to 0. So that would give me two values, which is what we want, okay. Cool, so let's do that. So firstly, this point, the first point, 4, 0, which is the first root, we need to move that to the origin. So that means we need to shift it. Well, if we're going from 4 to 0, let's have a look again on the graph. This point needs to move to the left by 4, okay? Oh. So we need to shift graph left by 4 units, okay? Well, then what does that mean then? Because remember, originally k is f of x plus k. That's where it comes from. So as a function then, I need to do the opposite inside the function. So instead of, if I'm shifting it left by 4, as you can see here, I need to subtract 4 to get from 4 to 0, right? Well, if I'm going to have to do the opposite then, so I'm going to have to do f of x plus 4, which means then I'm subtracting 4 to move it left by 4, which would then mean that therefore k would be positive 4, okay? Because f of x plus k is the 4 there, if you match it. Okay, so that's one value, but then the other point on the x-axis is here. This is minus 1.5. So then I need to move that to the right to 0, right? Okay, but then again, if I'm moving the minus 1.5 0 to 0, 0, I'm going to move it 1.5 to the right, okay? So I need to shift graph right, okay? right by 1.5 units. Okay, so that means I need to add x. I need to add 1.5 to x. So as a function, we need to do the opposite. So therefore, instead of adding x by 1.5 to move the graph to the right by 1.5, I need to do the opposite. So x minus 1.5 instead. Therefore, k would be minus 1.5. So those are our two values then of k. There we are. Cool. So those are the two values of k that I can put into this new function to shift the original curve f of x to then, in order for that new curve to pass through 0, 0, which is what the question's saying. Okay, cool. So that's translations. Hopefully you get the main idea, which we will be using throughout the course, is that what you do inside the function, so like f of x plus a, you instead of adding a to x, you do the opposite of subtracting, which means you go to the left. Then if you have a number outside the function, that affects the y, and anything outside the function, you do exactly what you expect. So you'd add a to y to then move it up by a. Cool. We'll be using that concept in the next section again, but for now, that's translations. So there we are. So I will leave that there then.